to speed up software transactional memory.
Okay, can everybody hear me?
Yes.
Okay. Okay, so today I'm going to be talking about some work that we've been doing on implementing partial aborts for transactional memory. Maybe. Okay, no remote. Okay, so traditional approaches to implementing concurrent programs have, for the most part, revolved around using locks. So in the last talk, we saw lock-free data structures, but essentially the same principle applies. If you take a coarse-grained approach, this is pretty lightweight, it's really easy to implement, but it doesn't scale well when you move to high contention workloads. On the other hand, you could take a fine-grained approach. This will give you good scalability and good performance, but it's notoriously difficult to implement. And on top of this, if you're using locks for both cases, you can take atomic operations, but they will not compose with other atomic operations. So this is where software transactional memory comes in. So it's essentially just as easy to use as coarse-grained locks. It has very little burden on the programmer, but is able to give you better performance somewhere in between these two ends of the spectrum. So essentially the idea here is we provide the programmer with this interface where they're allowed to wrap some arbitrary chunk of code in an atomic block. Okay, so the work we're presenting here is done in a project called Manicore. This is an implementation of standard ML that provides some support for concurrency and parallelism. So we're functional programmers. Instead, we're going to use higher order functions. So we have this atomic function, which takes in a function that gets executed atomically. And then inside these transactions, we have functions for reading from, writing to, and creating these trefs. And here a tref is like your traditional standard ML ref cell, but with a transactional semantics. So basically the idea is we're going to take these transactions and we're going to execute them optimistically. Okay, so we're not going to acquire any locks as we're executing them. Instead, when we get to the end, we'll just verify that we saw a consistent view of memory. Okay, if it turns out that we didn't see a consistent view of memory, we'll just restart the transaction from the beginning. And we'll keep doing this until we eventually get to a point where we did see a consistent view of memory. So there are many ways of enforcing atomicity for transactional memory. This is just one of them. But basically the idea is each thread is going to maintain its own private write set that only it has access to. So when you go to write to a tref, instead of modifying that memory location directly, we're going to record that this is the tref we want to modify, and this is the value that we want to write into it. Okay, so when we go to read from a tref, we're first going to check, have we made any local modifications to it? If so, we'll take our latest modification, and if it doesn't exist in our write set already, we'll read directly from the tref, and we're going to record this in our read set. Okay, when we get to the end of the transaction, we'll then walk our read set and make sure that for everything that we touched, it's the same as it was when we started our transaction. Okay. If it turns out that something has changed since we started our transaction, we'll just throw away the write set and we'll start over from the beginning. Otherwise, we saw a consistent view of memory, so we can commit our transaction by writing all of our local modifications into the trefs so that other concurrent transactions can see our effects. So in this example, here we have a linked list. Each node in this list is represented as a tref. And here we have two threads. One is looking to insert a node at position i+1, and a second thread is searching for a node at position n+1. So they both start marching down this linked list, and eventually we get to the point where thread 1 is ready to perform its insertion. So it does its thing, and it commits its transaction. Thread 2, on the other hand, has a little bit more work to do. So it eventually makes its way all the way down to the end of the list, and it's ready to return, but it needs to make sure that it saw a consistent view of memory. Unfortunately, it read something that has since changed from the time that it started its transaction, so thread 2 goes all the way back to the beginning. Okay, so this is unfortunate because we don't really need to redo the entire transaction to ensure that we saw a consistent view of memory. Instead, it would be nice if we could somehow get back to this point. Okay, so if we can get back to this point, we can retry our transaction a second time. We can shorten the time it takes to get to our commit point, and we can increase the likelihood that we'll get a chance to commit our transaction before somebody else comes along and causes us to abort again. So the subject of the work that we're presenting here at ICFP is how do we go about implementing partial aborts for transactional memory in an efficient way. Okay, so this has been attempted in the past in previous work, and basically the idea is that when we read from a TREF, like normal, we're going to look it up in our write set. If we get something back, we'll return whatever our local modification was. Otherwise, we're going to just pull out the value of the TREF, and then we're going to make a copy of the stack. Okay, so this is essentially is laying down a checkpoint in the transaction, and then we'll store this checkpoint in our read set. And so the idea here is that if this TREF later becomes out of date, we can get back to this point in the transaction by overwriting the stack with this checkpoint. Okay, and now we also will remember a pointer to what our write set looks like, so that that's consistent with this point in the transaction as well. So unfortunately, this has linear complexity in both time and space to make a copy of the stack. So doing this transparently every time you read a TREF is not feasible. So our idea is that since we're in a functional language, we can convert to continuation passing style. Okay, so now that we're in CPS, we have this incoming continuation K, and this represents the entire rest of the program. Okay, so when we invoke this continuation K, this is going to compute everything that remains to be computed in this program. So now we can take this continuation and we can store this in the read set, and we've now essentially performed the same sort of checkpointing that we saw on the last slide, but we can do it in constant time and in constant space. Okay, so assuming that we've already converted to continuation passing style, the amount of overhead necessary to support partial aborts compared to full aborts is essentially 16 bytes per read. Right? Before, all we needed to do was record the TREF that we're reading from each time we do a read. Now we just need 2 extra fields, one for the continuation and one for the pointer into our write set. So this should work really well, right? There's very little overhead, but yet should save us a lot of work when we end up aborting a transaction. Unfortunately, that was not the case. So we implemented this in Manicore, and we found that our partial abort implementation actually performs marginally worse than our full abort implementation. Okay, so this is strange, given that our partial abort implementation is aborting 2,000 fewer transactions than the full abort analog. Okay, and not only are we aborting 2,000 fewer transactions, these 9,150 re-executed transactions in the partial abort STM are partial transactions. So we're not even redoing the whole thing each time, whereas in the full abort, these 11,325 transactions, you're starting over from the very beginning each time. So given that we're doing so much less work in the partial abort STM, we end up allocating a lot less data. Okay, almost 30% less data. And so this here is where things get very strange. So despite the fact that we're allocating 30% less data, we're spending more than triple the amount of time in the garbage collector. Okay, so why is that? So if we look at the full abort implementation here of the read function, it takes in a continuation. Assuming we didn't find the TREF in our write set, we're going to pull out the value and record just the TREF in our read set. Then we're going to invoke the continuation. Okay, after we invoke this continuation, that's it. There are no more references to the closure for K. If we look at the partial abort implementation, by storing a pointer to this continuation in our read set, we're keeping this closure live throughout the entire duration of the transaction. Okay, so like in most other functional languages, in Manicore we're doing a form of generational garbage collection. So generational garbage collectors are very effective against this short-lived heap allocated data. So in the full abort implementation, this continuation is live for a very short amount of time. But in the partial abort implementation, we keep it around for a lot longer. So it ends up getting promoted to some of the older generations. So it's also worth noting that in Manicore, we're really doing a form of concurrent generational garbage collection. Okay, so basically the idea is that for each physical core on the machine, we have one of these processor abstractions we'll call a vproc. Okay, so each vproc has its own local heap that it can allocate in, and then there's a global heap that's shared by all the vprocs that we can promote data to if we need to share data, or if we run out of space in our local heap, we can move it up there. So these local heaps in the vproc structures, they can be collected concurrently. So if I run out of space on my vproc, I don't need to synchronize with anybody else to do that collection. Now, if we promote enough data into the global heap and we have to collect that, this becomes a stop-the-world collection, and we have to synchronize with everybody else in order to do this. So in the full abort implementation, when you have all of these return continuations that you allocate and then are immediately dead, you're able to clean these up in your minor collections in your non-synchronizing concurrent collections. Whereas in the partial abort implementation, since we're keeping them live for such a substantial amount of time, we end up promoting a lot of them up to the global heap. We do a lot more of these expensive global collections. So how do we solve this problem? So here we have a diagram of what our read set and our write set might look like for the scheme that I just described. So we have a pointer linking all these entries together. We have space for the tref, the corresponding continuation, and what the write set looked like at the time of performing that read. So basically what we're going to do is we're going to move from a linked list representation to a skip list representation. Okay, so we're going to add this extra field for the short path, and the invariant that we're going to enforce is that only entries on the short path are allowed to have a continuation. Okay, so and then the entries that are not on the short path will either have set their continuation pointer to null, or will have not recorded them in the first place. Additionally, we're going to introduce this frequency variable, and this is going to control how frequently we record continuations in our read set. Okay, we're also going to keep track of how many continuations we're keeping live in the read set, and then we're going to put a hard limit on how many we're allowed to hold on to. Okay, so in this example, our frequency starts out as 1. We already did one read to T1, and we recorded its continuation. We do a read again. We record the continuation. We do that a third time, and we do that a fourth time. Okay, so at this point, we have 4 continuations in our read set, and that's as many as we're allowed to hold on to. So what we're going to do is we're going to walk the short path of our read set, and for every other item, we're going to set the continuation pointer to null, and we're going to drop it from the short path. Okay, so this becomes our first victim. So we're going to set K3 to null, and we're going to swing that previous short path pointer around to the next guy. Okay, then this becomes our next victim. We're going to set K1 to null, and we're going to drop it from the short path. Okay, so now at this point, we've taken the number of continuations in our read set, and we've cut that in half. Additionally, what we're going to do is we're going to cut our frequency in half here. So from this point on in the transaction, we're only going to record our continuations at every other read. Okay, so now when we do a read, we're not going to record the continuation, and so there's no need to allocate space for those extra fields. Then we do another read, we will record that continuation, and we'll add that to the short path. And this process continues. So once we hit our limit, we'll do this filtering process where we drop every other checkpoint, and we'll cut our frequency in half yet again. So now when it comes time to validate our transaction, we'll walk the read set. As soon as we find something that's out of date, we're going to take everything that comes after that violated entry, and we're going to throw that away. Then we'll update our write set to whatever that entry is pointing to. Okay, so in this example, when we read from T4, TB and TA are what existed in our write set at that time. Okay, and then we're going to pull out the value from the tref, and we'll invoke the continuation K4. And at this point, this will restore the execution to exactly where we were at after having read from T4. So if we go back to this linked list benchmark that we saw earlier, if we add this continuation bounding approach on top of our partial abort STM, our execution time goes down substantially. We're aborting even fewer transactions, and our garbage collection time goes down substantially. So there are more results in the paper. The point that I want to make here is for the benchmarks that exhibit very large transactions, we're doing quite well. For those with medium length transactions, we're doing pretty all right. And for those that have really short transactions, it doesn't really hurt us. Okay. For red-black tree, we're not doing so hot here. There's a good explanation in the paper as to what's going on and a nice proposed solution as to how to fix this. So to wrap things up, this continuation bounding approach, the obvious advantage here is that it essentially solves the garbage collection problem that we saw earlier, but yet it's able to maintain an even distribution of checkpoints throughout our transaction. Okay, so regardless of where we find a violation in our transaction, chances are we'll be able to find a checkpoint that's somewhere in the neighborhood. Okay. Lastly, this is able to dynamically learn what the right frequency is to be recording these checkpoints in the transaction, regardless of the application and regardless of how you compose these transactions. Okay, so previous approaches have relied on programmers to manually insert these checkpoints, which you can imagine putting a checkpoint down manually might make sense in a particular context, but if you compose that transaction with another one, maybe that's not such a good place anymore. So being able to do this transparently and automatically allows us to get an even distribution regardless of the application, regardless of how we compose these things. So I'll stop here and take any questions.
That was very nice work. I really enjoyed it. I did see the number 4 kind of come out of nowhere. How do you know that 4 is the right bound to put on continuations, and might that bound change for a different application? So 4 is not what we're using in our actual implementation. That just seemed like a reasonable number for an example. For all the benchmarks we present in the paper, we chose 20. And we chose that somewhat arbitrarily. The thing is, so I don't think that it's application dependent. I think it's system dependent. So I think it's what do you set your heap size to? Your limit should maybe be somehow related to that.
Sometimes things look cheap because they are already paid for. Mm-hmm. So in your talk, you said, assuming we are using CPS, blah, blah, blah. So do you know how much CPS costs you compared to a more direct style implementation? Because after all, the reason you capture a continuation is cheap is because the continuation is already in the heap.
Yeah.
Right? What direct style implementations would use a stack, effectively they're stack allocated. There's a built-in garbage collector on the stack. So you're placing extra load of the garbage collector, maybe more memory traffic, who knows what kind of carry on. So you're making a penalty for that. So the question is, how much is that? And if you took all that back, right?
Yeah.
If you recovered that, then how would the numbers look?
So that's a good question. So for Manicore, I have no idea. We're CPS converting not just to support this. So
I know there are many other advantages.
Yeah, right. So in the context of parallelism and concurrency, continuations are a pretty handy thing to have around. So I mean, the first class continuations in Manicore are a fundamental part of our thread scheduling infrastructure, and they're all over the runtime system. So really, we're just taking advantage of something that was already there. So something that we've been working on since having submitted this paper is doing this in GHC, where we use a CPS monad instead. So now you're not CPS converting everything, basically just your transactions in CPS. So stuff that's outside the STM monad, and even pure computation inside the STM monad stays in direct style. So you don't do all this short-lived heap allocation, but you still get enough power to do the partial aborts.
Okay, so then you could do a head-to-head comparison.
Then you could do a
That would be quite interesting, yeah. Thanks.
Yeah.
Quick question.
Yeah, so I was wondering, you probably tried this, and I'm curious what happened, which is, what happens if you just try to make the local heap big enough so that you can survive the transaction before you run out of space?
So interestingly enough, we did not try that. So in Manicore, it's really the local heap size that's important here. So in Manicore, the local heap size is really baked into the runtime system in a way that would be very unpleasant to modify. So we can change the global heap size pretty easily, but the local heap size is kind of stuck. So to be honest, I actually don't have an answer to that question. I mean, okay, so I mean, if you can keep it large enough that you have enough space for the continuations for your entire transaction, chances are our numbers will look a lot better.
All right, let's thank the speaker.